Close your eyes for a moment and picture the room you're in. The walls, the ceiling, the weight of your body against whatever surface holds you. You know this room. You remember walking into it. You remember the day before, and the week before that, and a whole life stretching backward. Childhood, faces, meals you have eaten, conversations you have had. All of it feels solid. All of it feels real. Now consider this. There is a number. It is a probability, calculable, testable in principle, and it says that in a universe old enough and empty enough, the most likely way for a mind like yours to exist is not through billions of years of stellar evolution and planetary chemistry and the long crawl of Darwinian selection. The most likely way is for that mind, complete with all its memories, all its sensations, all its quiet certainties about where it came from, to simply fluctuate into existence from the random jitter of particles in a void, to appear, fully formed, for a fraction of a second, and then dissolve. The memories would be false, the room would be false. The life you think you lived would be a hallucination written into neurons that assembled themselves by accident and will scatter before the next thought completes. This is not a thought experiment invented to unsettle you. This is a conclusion that follows, with uncomfortable rigour, from physics we already trust. It has a name. Physicists call it the Boltzmann brain problem. And the reason it matters, the reason some of the most careful cosmologists of our time have spent years trying to design universes that avoid it, is that if the math is right, you are almost certainly one of them. Tonight we're going to follow this idea from its strange origin in the steam engines of the 19th century to the emptiest reaches of a universe that may never end. We will meet the men and women who first saw the problem, who tried to dismiss it, and who eventually realised it could not be dismissed. We will ask what it would mean if the universe is structured in such a way that most observers, most minds, most experiences of being are brief thermal accidents rather than the products of history. And we will ask whether there is any way out. If this is the kind of slow, careful journey that helps you think or helps you rest, consider tapping the like and subscribe button. It costs nothing, and it helps these videos reach others who might want them. Now, let us begin. The story starts in Vienna, in the second half of the 19th century, in a city that smelled of horse manure and coal smoke and the faint sweetness of the bakeries that lined its older streets. The Austro-Hungarian Empire was at its height. Franz Joseph sat on the throne. The Ringstrasse was being built, a grand boulevard circling the old city, and along it rose new palaces of culture, the Opera House, the Art Museum, the University. It was a city that believed in progress, in the steady accumulation of knowledge, in the capacity of the human mind to understand the machinery of the world. And in a cramped office at the University of Vienna, a man named Ludwig Boltzmann was trying to understand something that should have been simple. Why does heat flow from hot to cold? You know the answer intuitively. You have felt it your whole life. A cup of coffee cools, a block of ice melts in your hand. If you touch a hot stove, the heat moves into your skin, not the other way around. This is so obvious, so universal, that it hardly seems like the kind of thing that would require explanation. Heat flows downhill. That is just what heat does. But Boltzmann was not satisfied with just what heat does. He wanted to know why. He wanted to derive the behaviour of heat from the behaviour of the tiny particles, the atoms and molecules, that he believed made up all matter. And when he tried to do this, he ran into a wall. The problem was this: the laws of physics, as they were understood in Boltzmann's time, did not care about the direction of time. Newton's equations, which governed the motion of particles, worked just as well backward as forward. If you filmed a collision between two billiard balls and played the film in reverse, the physics would look perfectly normal. There was nothing in the fundamental laws that said the future had to be different from the past. And yet heat only flowed one way. The future was different from the past. Eggs broke and did not unbreak. Coffee cooled and did not spontaneously reheat. The universe, at every moment, was doing something that the laws of physics said it did not have to do. Boltzmann's answer was radical. He proposed that the second law of thermodynamics, the law that says entropy always increases, that disorder always grows, that heat always flows from hot to cold, was not a fundamental law at all. It was a statistical law. It was what happened almost all the time in almost all circumstances because of the sheer number of particles involved. but it was not absolutely required. It was not baked into the structure of reality. It was just overwhelmingly, stupendously, almost unimaginably probable. Let that settle for a moment. What Boltzmann was saying was this: when you see your coffee cool, what you're really seeing is the transition from a relatively rare state, one in which the fast-moving molecules are concentrated in the coffee and the slow-moving molecules are concentrated in the air, to a much more common state, one in which the fast and slow molecules are mixed together. There are vastly, incomprehensibly more ways for the molecules to be mixed than for them to be sorted. So when you start with a sorted state, the molecules will almost certainly move toward a mixed state simply because there are so many more mixed states to move into. This was entropy, not a mysterious force pushing toward disorder, just the overwhelming weight of probability. The universe was not commanded to increase its entropy. It just did, because the alternatives were so rare. But here is the thing about statistics. Rare is not the same as impossible. If you shuffled a deck of cards 1,000 times, you would almost certainly never see them come out in perfect order, ace through king, suit by suit. The odds against it are astronomical, but they are not zero. If you shuffled long enough, if you had an eternity to shuffle, eventually you would see that perfect order appear. Not because anything special happened, not because of any force or intention, just because you waited long enough for the improbable to happen. Boltzmann understood this. He understood that his statistical explanation of entropy came with a strange corollary. If you waited long enough, entropy could go down, heat could flow backward, eggs could unbreak. Not because the laws of physics changed, but because eventually, given infinite time, even the most improbable fluctuations would occur. And this is where the trouble began. Imagine the universe as Boltzmann pictured it, a vast, eternal sea of particles, bumping and jostling and exchanging energy, settled into a state of maximum entropy. This is what physicists call thermal equilibrium. It is the end state of everything. All the energy spread out evenly, all the gradients flattened, nothing happening, nothing changing, a uniform lukewarm fog extending forever in all directions, the heat death of the universe. In this state, nothing interesting can happen. There are no stars because stars require concentrations of matter and energy. There are no planets, no chemistry, no life. Just particles drifting in an endless bath of background radiation, occasionally bumping into each other, never creating anything new. But Boltzmann knew that even in equilibrium, small fluctuations would occur. A few particles over here would randomly clump together. A few over there would move a little faster than average. Most of these fluctuations would be tiny and would dissolve instantly. But given infinite time, larger fluctuations would happen too. Occasionally, by pure chance, a region of lower entropy would appear, a region where matter and energy were temporarily concentrated, where something interesting could happen before it all dissolved back into the fog. Boltzmann speculated that perhaps this was the answer to a question that had nagged at physicists. Why does the universe today have such low entropy? Why is there structure, stars, galaxies, planets, life, when the most probable state is featureless equilibrium? Maybe, he suggested, the universe as a whole was already in equilibrium. Maybe it had been in equilibrium forever. And maybe what we called our universe, the stars and galaxies we observed, the history we thought we remembered, was just a local fluctuation, a temporary dip in entropy that had happened by chance and would eventually dissolve back into the background. It was a strange idea, but it had a certain elegance. It explained why we found ourselves in a low entropy state without requiring any special initial conditions. We were here because low entropy regions were the only places where observers could exist. It was a kind of early anthropic reasoning. We see a special universe because only a special universe could produce us. But there was a problem, a devastating problem, and Boltzmann, for all his brilliance, either did not see it or chose not to dwell on it. The problem is this: if you are waiting for random fluctuations to produce a low entropy region, what is the most likely fluctuation you will see? Think about it carefully. A fluctuation that produces an entire galaxy, with billions of stars, trillions of planets, the whole sweep of cosmic structure, requires an unimaginably precise arrangement of particles. The odds against it are beyond astronomical. They are numbers so large they have no intuitive meaning. If you wrote them out, the digits would stretch from here to the edge of the observable universe and back again millions of times over. But a fluctuation that produces just one small object, a brain, say, or even a single moment of conscious experience, requires far less. It is still stupendously improbable, but it is stupendously less improbable than a whole universe. And here is the key. In an eternal universe at thermal equilibrium, you have infinite time. Given infinite time, all fluctuations will eventually occur, but the smaller fluctuations will occur vastly more often than the larger ones. For every fluctuation that produces a galaxy, there will be an inconceivably larger number of fluctuations that produce just a brain, a momentary cluster of particles that happens, by chance, to be configured in the right way to have an experience. These brains would not have real histories. They would have false memories, memories that appeared in the same instant the brain itself fluctuated into existence. They would remember childhoods that never happened, friends they never met, lives they never lived. They would have all the sensations of being real, continuous observers, but they would be illusions, thermal accidents, ghosts assembled by randomness and dissolved a moment later. And if this is how the universe works, if we are embedded in an eternal thermal equilibrium that occasionally fluctuates observers into existence, then almost all observers in the universe would be of this type, not the products of evolution, not the inheritors of a real cosmic history, just momentary fluctuations, vastly more numerous than the real thing, each one convinced it was real. You're an observer, you have memories of a past, you believe you're sitting in a room that exists in a universe that had a big bang and a long history and a future you will live into. But if Boltzmann's reasoning holds, the odds are overwhelming that you are wrong. The odds are that you're one of the fluctuations, that your memories are false, that the room around you is not real, that you will dissolve in an instant never knowing the difference. This is the Boltzmann brain problem. Say the name slowly, Boltzmann brain. It sounds almost whimsical, like something from a children's story, but the physics behind it is relentless. Let me try once more to give you a feel for the numbers involved. Imagine you're watching an endless desert of gas at thermal equilibrium. The heat death of the universe stretched out before you. Nothing is happening. Particles drift. Energy is spread uniformly. You wait. Every so often, purely by chance, a few particles clump together. Most of these clumps are tiny. A handful of molecules form a fleeting structure and then scatter. You keep waiting. After an inconceivable span of time, trillions of years, you see something larger. A small crystal forms spontaneously. It exists for a moment and then dissolves. You wait longer. After an even vaster span of time, you see something more complex. A chain of molecules that resembles for one flickering instant a fragment of DNA. It is not alive, it is not functional, but it is recognizably structured, and then it is gone. Now extrapolate. Keep waiting. Let the numbers grow so large that human intuition fails entirely. After a span of time that cannot be named, a number of years written with more digits than there are atoms in the observable universe, you will see, by pure chance, a fluctuation that assembles something more, a cluster of matter configured, for one instant, like a functioning brain, a brain with neurons, with electrochemical signals, with, for that instant, the experience of being. What does that brain experience? It experiences whatever the random configuration of its neurons happens to encode. It might experience terror, it might experience peace, it might experience a vivid memory of walking through a forest on an autumn day, the smell of leaves, the sound of footsteps, the face of a loved one. All of it false, all of it generated by accident, all of it dissolving in the next instant as the particles scatter. This is not science fiction. This is thermodynamics. Given enough time, it must happen. The question is not whether Boltzmann brains are possible. The question is whether they are common. And the answer, if the universe is eternal and tends toward thermal equilibrium, is that they are not just common. They are the dominant form of conscious experience in the cosmos. Rest with that for a moment. For decades after Boltzmann's death, he took his own life in 1906, possibly in part because of the attacks on his atomic theory. The Boltzmann brain problem lay dormant. Physics moved on. Quantum mechanics arrived. Relativity arrived. The structure of the atom was revealed. The Big Bang was discovered. The universe, it turned out, was not eternal in the way Boltzmann had imagined. It had a beginning 14 billion years ago in a state of extraordinarily low entropy. This seemed, for a while, to make the whole worry irrelevant. We were not fluctuations in an eternal equilibrium. We were the products of a real history, a real expansion, a real cooling from a hot, dense state. But the problem did not go away. It transformed. In the late 20th century, cosmologists began to grapple with a new discovery. The universe's expansion was accelerating. Something, a repulsive energy embedded in the fabric of space-time itself, was pushing galaxies apart at an ever-increasing rate. This energy was given a name, dark energy, and its most natural interpretation was that it was the cosmological constant, a fixed energy density that pervaded all of space and would persist forever. If this is true, if dark energy is constant, then the universe has a future very different from the one earlier physicists imagined. It will not collapse back on itself. It will not cool smoothly into heat death. Instead, it will expand forever, diluting all matter and radiation until only the dark energy remains. Galaxies will recede from each other faster than light can travel between them. Stars will burn out, black holes will evaporate, and what is left will be a state called de Sitter space. Empty, cold, pervaded by a faint quantum fizz of virtual particles stretching to eternity. De Sitter space is not thermal equilibrium in the ordinary sense, but it has something analogous, a temperature. The expansion of space itself creates a horizon, a boundary beyond which light can never reach you, and that horizon radiates faintly like a black hole. The temperature is unimaginably low, a tiny fraction of a degree above absolute zero. But it is not zero, and that means fluctuations can still occur. Here, in the far future of our universe, the Boltzmann brain problem returns with a vengeance. The physicist who brought this into sharpest focus was Carroll, a cosmologist at Caltech and later at Johns Hopkins, known for his ability to take the most abstract problems in physics and explain them clearly without losing their rigor. In the early 2000s, Carroll and his collaborator Jennifer Chen published a paper that grappled directly with the question of entropy and the arrow of time. They wanted to understand why the universe began in such a low entropy state, why there was a Big Bang at all rather than just eternal equilibrium. But in the course of their work, they ran headlong into the Boltzmann brain problem. The issue was this: if the universe is going to expand forever, and if it will eventually reach a de Sitter state with a tiny but non-zero temperature, then that state will persist for eternity. And in eternity, everything that can happen will happen. Small fluctuations will occur constantly. Large fluctuations will occur less often but will still occur given enough time. And the largest fluctuations, the ones that produce entire galaxies, entire histories, entire civilizations, will be vanishingly rare compared to the smaller fluctuations that produce single brains. Carroll did the math. Others did the math. The numbers were not ambiguous. In an eternal de Sitter universe, the ratio of Boltzmann brains to ordinary observers like us, who arose through the conventional process of stellar evolution and biological development, is not 10 to 1. It is not 1 billion to 1. It is infinity to 1. For every real observer with a genuine past, there are infinitely more fake observers who merely think they have a past. And this is not a marginal result. It follows directly from two things physicists generally accept: that the universe will reach a de Sitter state, and that the laws of quantum mechanics allow fluctuations. You cannot reject the conclusion without rejecting one of those premises. Let me put that in perspective. You are reading or listening to this now. You believe you are a normal human being on Earth, in a universe with a 14 billion year history, on a planet with a 4.5 billion year history, in a body that developed over decades from a single cell. You believe your memories are real. You believe the room around you is real. But if the standard cosmological model is correct, if dark energy is constant and the universe will expand forever, then the overwhelming majority of observers who believe exactly what you believe are wrong. They are Boltzmann brains, their memories are false, their certainty is misplaced, and there is no way to tell the difference from the inside. This is the point where reasonable people ask, why should I care? Maybe most observers in the far future will be Boltzmann brains, but I am not in the far future. I am here now in the early universe, when structure still exists and history is real. Why does some hypothetical future infinity matter to me? The answer lies in probability, and it is the part that makes cosmologists genuinely uncomfortable. When we do science, we rely on a principle that seems obvious but turns out to be treacherous. We assume that we are typical observers. We assume that our observations are likely to be representative of what most observers would see. This is called the typicality assumption, or sometimes the principle of mediocrity. It is the foundation of all statistical reasoning. If you want to know the average height of humans, you measure a sample and assume your sample is not wildly unusual. If you want to know the properties of the universe, you make observations and assume your observations are not wildly unusual. But here is the problem. If almost all observers in the history of the universe are Boltzmann brains, then you are almost certainly a Boltzmann brain. That is what typicality says. If 99% of observers are fluctuations, then the probability that you are a fluctuation is 99%. And the math says the proportion is not 99%. It is infinitely close to 100%. This means that if you take the standard cosmological model seriously, and if you take the typicality assumption seriously, you should conclude that your memories are false and your observations are unreliable. But that's absurd. Your observations are the foundation of the science that led to the cosmological model in the first place. If you cannot trust your observations, you cannot trust the model. The reasoning eats itself. This is what philosophers call a reductio ad absurdum. The conclusion is so unacceptable that it forces us to reject one of the premises. But which premise? There are several options, and cosmologists have debated them for years. One option is to reject the typicality assumption. Maybe we should not expect to be typical observers. Maybe we should instead expect to be early observers, or causally connected observers, or observers weighted by some other criterion. Various proposals have been made along these lines, but none has gained consensus. The problem is that without some version of typicality, statistical reasoning falls apart entirely, and it is not clear what should replace it. Another option is to reject the model. Maybe dark energy is not constant. Maybe the universe will not expand forever. Maybe something will happen. A phase transition, a change in the laws of physics, a big crunch that prevents the eternal de sitter future from ever occurring. This is a tempting escape, but it requires positive evidence that we do not yet have. You cannot simply wish away a cosmological constant because you do not like its implications. A third option is to take the problem seriously and design cosmological models specifically to avoid it. This is in fact what many cosmologists have done. When they evaluate multiverse theories, eternal inflation scenarios, or other speculative models of the cosmos, one of the criteria they apply is, does this model produce more Boltzmann brains than ordinary observers? If it does, the model is in trouble. This is sometimes called the Boltzmann brain criterion, and it is treated as a genuine theoretical constraint, not just a philosophical curiosity. Think about what that means. The Boltzmann brain problem is so severe, so difficult to dismiss, that it has become a design specification for theories of the universe. Cosmologists are building models of reality, models of where we came from and what kind of universe we inhabit, and they are rejecting otherwise plausible models on the grounds that those models would make us almost certainly fake. Let that settle for a moment. The physicist Andreas Albrecht, working at UC Davis, has been one of the most persistent voices on this issue. Albrecht was one of the architects of inflationary theory in the 1980s, a theory that explains the uniformity and flatness of the universe by proposing a brief period of exponential expansion in its earliest moments. But decades later, Albrecht turned his attention to the Boltzmann brain problem, and what he found disturbed him. Albrecht argued that the problem was not just a technicality, it was a threat to the foundations of scientific reasoning. If we cannot trust that we are ordinary observers, if our default assumption must be that we are thermal fluctuations, then we cannot trust our observations, and if we cannot trust our observations, we cannot do science. The Boltzmann brain problem, taken seriously, undermines the entire enterprise. His solution was radical. He proposed that cosmological models should be judged in part by whether they produce a universe in which the Boltzmann brain problem does not arise. This is a different kind of constraint than physicists are used to. It is not a constraint from observation. We have not observed Boltzmann brains, nor could we. It is a constraint from the preconditions of rational inquiry. A universe in which most observers are deceived is a universe in which science is impossible. Therefore, if we believe science is possible, we must believe we are not in such a universe. This is a strange kind of reasoning. It feels almost circular. But Albrecht and others have argued that it is no different from the way we trust our senses in the first place. We assume our eyes report the truth, not because we have proven it, but because the alternative makes all further reasoning pointless. The Boltzmann brain criterion is, in this view, an extension of the same foundational assumption. But not everyone is satisfied with this escape. Some physicists have argued that the problem reveals a deeper flaw in how we think about cosmology. Maybe the question, what would a typical observer in this universe see, is simply not a well-defined question. Maybe the universe is too vast, too infinite, too varied to admit of meaningful statistical reasoning on these scales. This is sometimes called the measure problem in cosmology, and it remains unsolved. Here is what the measure problem looks like. Suppose the universe is infinite. Suppose there are infinitely many galaxies, infinitely many stars, infinitely many planets. On some of those planets, ordinary observers evolved through Darwinian processes, but in the far future, Boltzmann brains fluctuated into existence in de Sitter space. How do you compare the number of ordinary observers to the number of Boltzmann brains when both numbers are infinite? You might think you can take a ratio, infinity divided by infinity. But that is not how infinity works. The ratio depends on how you count. If you count all the observers that exist at any time, you get one answer. If you count only the observers that exist within a certain spatial region, you get a different answer. If you weight observers by their duration or by their causal connections to the Big Bang, you get still different answers. There is no neutral, obvious way to count. And the Boltzmann brain problem is, in many ways, a problem about counting. This does not make the problem go away. It makes it worse. It means we do not even know how to formulate the question rigorously, let alone answer it. And yet the question will not stop nagging. Because if you take the physics seriously, the fluctuations will happen. The brains will appear, and they will outnumber us by any reasonable measure, unless we find a reason to think the future is different than we expect. Picture again the universe as it will be, trillions upon trillions of years from now. The stars are gone. The galaxies have faded beyond every horizon. What remains is an ocean of dark energy, a faint quantum hiss at a temperature barely above absolute zero, and time stretching forward without limit. In this ocean, every so often, a ripple forms. Most ripples are small. They rise and fall in an instant. But sometimes, very rarely, a ripple takes shape. Particles align, structures emerge, and for one flickering moment, something experiences. It experiences warmth, perhaps. It experiences memory. It experiences the conviction that it is real, that it has a history, that the moment before this moment was part of a longer story. And then the ripple dissolves. Was that mind real? Was that experience genuine? By what measure do we call our experience, here, now, in what we believe to be the early universe, more real than those flickering moments in the void? These are not questions science can answer, but they are questions science has forced us to ask. And as we continue this journey, we will ask what would happen if we took them seriously. We will ask whether the math can be changed. We will ask whether the escape routes hold. And we will ask quietly what it feels like to sit with the possibility that we do not know, cannot know perhaps, whether we are the originals or the echoes. The night is long, the questions run deep, and we have only begun. Let us begin with a number, 10 to the power of 10 to the power of 69. That is not a typo, that is not a misprint. That is a number so large that even writing it down in its full decimal form would require more digits than there are particles in the observable universe. More digits than there are Planck volumes in the entire cosmic horizon. More digits than any physical process could ever inscribe on any surface in any conceivable future. And that number is an estimate, a rough conservative estimate, of how long you would have to wait on average for a Boltzmann brain to fluctuate into existence in de Sitter space. Say it again, slowly. 10 to the 10 to the 69 years. The current age of the universe is about 14 billion years. That is 10 to the 10th power. The time until the last stars burn out is perhaps 10 to the 14th years. The time until the last black holes evaporate through Hawking radiation is 10 to the 100th years, a Google years, a number so large it gave a search engine its name. And still, we have not come close to 10 to the 10 to the 69. This is the timescale that haunts modern cosmology. This is the clock that ticks beneath the Boltzmann brain problem. Because the question is not whether these fluctuations will happen. The physics says they will. The question is whether the universe lasts long enough for them to matter, and if the universe is eternal, if dark energy persists forever, if de Sitter space stretches on without end, then the answer is yes. The universe lasts long enough. The fluctuations accumulate, and eventually, inevitably, they dominate. This is not speculation. This is arithmetic applied to our best physical theories, and it is the arithmetic that keeps cosmologists awake. To understand why this matters, we need to look more closely at the vacuum itself, not the vacuum of everyday speech, not the absence of air, not the emptiness of a sealed jar, the quantum vacuum, the fabric of space when every particle has been removed, every field has settled to its lowest energy state, and nothing in the ordinary sense remains. This vacuum is not empty. It cannot be empty. Quantum mechanics forbids it. The uncertainty principle tells us that we cannot know both the value of a field and the rate at which it is changing with perfect precision. If space were truly empty, if every field were exactly zero and exactly still, we would know both. We would violate the fundamental limits of knowledge that quantum mechanics imposes, and so the fields cannot be exactly zero. They fluctuate, they jitter, they foam. This is sometimes called zero-point energy. The vacuum hums with it. Even at absolute zero, the fields are restless. In most contexts, this restlessness is negligible. It produces tiny effects. The Casimir force between metal plates, small shifts in atomic energy levels, subtle corrections to particle masses. Physics has measured these effects with extraordinary precision. They are real, they are there, but they are small. In de Sitter space, they are not small. De Sitter space is the technical name for a universe dominated by a positive cosmological constant. A universe like ours, in the far future, after the stars have died and dark energy has won. In such a universe, space expands exponentially. Every point recedes from every other point faster and faster, until a cosmic horizon forms, a boundary beyond which light can never reach you, no matter how long you wait. Inside this horizon, the vacuum fluctuates. And here is the key insight, the result that Ludwig Boltzmann could not have known, but that modern physics has derived from first principles. The fluctuations in de Sitter space are thermal. The vacuum has a temperature. It is a tiny temperature, roughly 10 to the minus 30 Kelvin, so cold that even the cosmic microwave background at 2.7 Kelvin is a blazing furnace by comparison. But it is not zero. And in physics, a temperature above zero means thermal fluctuations. It means particles appearing and disappearing. It means energy borrowed from the vacuum and returned an instant later. It means, over long enough timescales, structures assembling from pure chance. This is not poetry. This is the Gibbons-Hawking temperature, derived in 1977 by Gary Gibbons and Stephen Hawking, and it follows directly from the mathematics of quantum field theory and curved spacetime. The same mathematics that predicts Hawking radiation from black holes predicts thermal radiation from the cosmological horizon. The de Sitter vacuum glows, and if it glows, it fluctuates, and if it fluctuates, it creates. Now let us ask the question that Ludwig Boltzmann asked in the 19th century, but in this new context. Suppose you have a thermal system at equilibrium. Suppose it has a temperature, any temperature, no matter how low. How long would you have to wait for a fluctuation large enough to produce a given structure? The answer depends on the entropy of that structure. The more organized the structure, the lower its entropy and the rarer the fluctuation required to produce it. A single particle appearing from the vacuum is common. A pair of particles is rarer. A cluster of particles arranged in a specific pattern is rarer still. And a functioning brain, a network of 100 billion neurons, each connected to thousands of others, each firing in precise temporal coordination, is so improbable that the waiting time stretches beyond imagination, but not beyond infinity. And that is the problem. In a universe that lasts forever, every finite waiting time is eventually reached. Every improbable fluctuation eventually occurs, and the fluctuation that assembles a conscious brain, complete with memories, with the experience of a coherent life, with the conviction that it is real, is one such fluctuation. The number 10 to the 10 to the 69 is a rough estimate of this waiting time, but the exact value does not matter. What matters is that it is finite, and in an eternal universe, finite waiting times guarantee occurrence. The brains will appear. Let that settle for a moment. We are not talking about a hypothetical scenario. We are not talking about a thought experiment designed to test philosophical intuitions. We are talking about a prediction of our best physical theories. If dark energy persists, if de Sitter space is the final state of the cosmos, then Boltzmann brains are a physical consequence of the mathematics. And they are not rare, they are common. This is the second counterintuitive claim, and it is perhaps harder to accept than the first. The first claim is that random fluctuations can produce conscious observers. The second claim is that given enough time, these observers outnumber us. Here is why. Ordinary observers, organisms like us, evolved through billions of years of Darwinian selection, exist only during a narrow window of cosmic history. We require stars, which burn for billions of years. We require planets, which form in the debris of stellar explosions. We require liquid water, stable chemistry, long timescales for natural selection to operate. All of this exists only while the universe is young, while matter is clumped, while the cosmos is far from equilibrium. That window is closing. In a few trillion years, the last stars will burn out. The raw materials for new stars will be exhausted. The universe will settle into the long, cold de Sitter phase, and no new ordinary observers will ever arise. But the Boltzmann brains are not bound by this window. They require only the vacuum. They require only fluctuations, and the vacuum will persist forever. So count with me. Ordinary observers exist for perhaps 10 to the 14th years, 100 trillion years, the maximum lifetime of the stelliferous era. Boltzmann brains exist for the entire duration of de Sitter space, which, if dark energy is a true cosmological constant, is literally infinite. 100 trillion years divided by infinity is zero. The ordinary observers are a vanishing fraction. The Boltzmann brains, flickering in and out of existence across the eternal void, are the overwhelming majority. And if you ask, what is a typical conscious experience in this universe? The math says, a Boltzmann brain. Not a human. Not an evolved organism, a fluctuation. Now picture what such a fluctuation would experience. You wake, though wake is not quite the right word, because there is no sleep before this moment. You simply exist, suddenly, completely, in the middle of a thought. You have memories. You remember breakfast. You remember a conversation with a friend. You remember the feeling of sunlight on your face, the texture of a wooden table under your hands, the scent of rain on pavement. None of it happened. The memories are false. They were assembled by the same fluctuation that assembled you. The sunlight, the table, the rain. None of them exist in the void around you. You are a pattern of particles that momentarily holds together in a configuration that produces the experience of being human, and in a fraction of a second, you will dissolve. You will never know. The dissolution is too fast for experience. The thought completes itself and then nothing. Was that experience real? In what sense did that flickering moment of consciousness exist? And here is the question that cuts deeper. In what sense is your experience right now any different? This is the question that Carroll and his collaborators have wrestled with in paper after paper. It is the question that drives the Boltzmann brain problem from a curiosity to a crisis. The issue is not metaphysical, it is epistemological. It is about what we can know. You believe you have a history. You believe you evolved on a planet orbiting a star in a galaxy in an expanding universe. You believe the Big Bang happened, that the laws of physics are consistent, that your memories correspond to actual events. But if Boltzmann brains are the typical observers in this universe, then most observers who believe exactly what you believe are wrong. Their memories are false. Their reasoning is flawed. Their entire cognitive apparatus was assembled by chance, and there is no reason to think it corresponds to reality. And if most observers who believe what you believe are wrong, then what grounds do you have for thinking you are the exception? This is not solipsism. This is not the Matrix. This is a statistical argument applied to cosmology, and it has a sharp logical form. Here is the argument. Premise 1. If a theory predicts that most observers are Boltzmann brains, then most observers who believe that theory are Boltzmann brains. Premise 2. Boltzmann brains have no reason to trust their reasoning, because their cognitive apparatus was assembled by chance. Conclusion: if you believe a theory that predicts Boltzmann brain dominance, you have no reason to trust your belief in that theory. This is called cognitive instability. The theory undermines itself. Believing it gives you grounds for disbelieving it. And our current best cosmological theories, the ones that predict an eternal de sitter future, appear to have this property. Now rest with that for a moment. The claim is not that our cosmological theories are wrong. The claim is that if they are right, we cannot rationally believe them. There is something self-defeating about a theory that predicts that most believers of the theory are mistaken. This is why physicists take the Boltzmann brain problem seriously. It is not a puzzle about distant futures or exotic fluctuations. It is a puzzle about the logical coherence of our entire cosmological framework, and it has led to a remarkable development. Cosmologists now design theories specifically to avoid Boltzmann brain dominance. This is not a side constraint. This is not a philosophical preference. This is treated as a physical requirement. A cosmological theory that predicts more Boltzmann brains than ordinary observers is, by this criterion, ruled out. Not by observation, but by the demand that our theories be rationally believable. Andreas Albrecht at UC Davis has been one of the most vocal proponents of this view. He argues that Boltzmann brain avoidance should be treated as a fundamental constraint on cosmological model building, on par with constraints like consistency with observation or mathematical coherence. This is a striking claim. It says that the problem of other minds, or rather the problem of typical minds, is not merely a philosophical curiosity. It is a guide to physics. It tells us something about which universes are allowed. Let us trace one example of how this works in practice. The simplest model of dark energy is a cosmological constant, a fixed energy density of empty space that never changes. This model fits the data beautifully. It explains the acceleration of the universe with a single parameter. It is elegant, and it predicts Boltzmann brain dominance. If the cosmological constant is truly constant, if it persists forever, then de sitter space lasts forever. The vacuum fluctuates forever, and the brains accumulate without limit. So cosmologists have explored alternatives. What if dark energy is not constant? What if it changes over time? One possibility is that dark energy decays. Perhaps the cosmological constant is not a constant at all, but a field, sometimes called quintessence, that slowly rolls down a potential energy slope. Eventually it might reach a state of zero or negative energy. Space would stop expanding exponentially, de sitter space would end, and the infinite future that generates Boltzmann brains would be cut off. This is not an ad hoc fix. There are theoretical reasons to consider dynamical dark energy. String theory, in many of its formulations, suggests that the landscape of possible vacua is vast and complicated, and that our current vacuum might be metastable, a temporary state that will eventually decay to something else. If the vacuum decays, the Boltzmann brains lose. The future is finite, the fluctuations are limited, and ordinary observers, arising during the brief window of cosmic history when stars burn and planets form, remain the majority. This is an escape route, and it is one that physicists take seriously precisely because it avoids the self-undermining conclusion. But the escape is not clean. The decay of the vacuum is not a gentle transition. In most models, it is a catastrophe. A bubble of true vacuum nucleates somewhere in space and expands at nearly the speed of light. Everything inside the bubble, every particle, every atom, every structure, is destroyed and replaced by the new vacuum state. This is called vacuum decay, and it is, in a sense, the end of everything. If you are inside the bubble, you do not see it coming. The wall of the bubble travels at nearly the speed of light. You have no warning. One moment, you exist in a universe with stars and galaxies and the laws of physics you have always known. The next moment, no moment. The physics inside the bubble is different. The particles you're made of may not even exist there, so the escape from Boltzmann brains requires accepting that the universe will eventually destroy itself. The question is only when. Current estimates suggest that if our vacuum is metastable, the decay timescale is extraordinarily long, perhaps longer than 10 to the 100 years, far longer than the lifetime of the stars, far longer than the evaporation of black holes, but not infinite. And if the decay happens, it happens everywhere eventually. The bubble nucleates, expands, consumes, and nothing remains. This is perhaps a grim comfort. The universe ends, and so the paradox is avoided. But it is a comfort of a sort. It means our current experience, our memories, our reasoning, our sense of a coherent history is likely genuine. It means we are probably not Boltzmann brains. It means the past is probably real. Probably. There is another escape route, and it is stranger still. Some physicists have argued that the Boltzmann brain problem arises from a hidden assumption that we should think of ourselves as typical observers. This assumption is sometimes called the self-sampling assumption, and it underlies most reasoning in cosmology about what we should expect to observe. But what if we are not typical? What if the question, what would a typical observer see, is simply the wrong question to ask? This is a subtle point, and it requires careful handling. The self-sampling assumption says that you should reason as if you were randomly selected from the set of all observers who share your observations. If most such observers are Boltzmann brains, you should conclude that you are probably a Boltzmann brain. But some philosophers and physicists have argued that this assumption is not justified. Perhaps you should reason only about observers in your causal past, observers who could, in principle, have influenced your existence. Boltzmann brains in the far future are not in your causal past. They have no connection to you. Why should they enter into your probabilistic reasoning? This is called the causal diamond approach, and it has been developed by several researchers, including Raphael Bousso at Berkeley. The idea is to count only observers within your cosmological horizon, the region of space-time that can causally influence you or be influenced by you. Within the causal diamond, ordinary observers vastly outnumber Boltzmann brains. The diamond is finite, the fluctuations are rare, and the conclusion changes. But this escape is controversial. It depends on accepting a particular approach to probability in cosmology, an approach that others find unmotivated or arbitrary. The measure problem, the question of how to count observers in an infinite universe, remains unsolved, and different measures give different answers. Here then is where we stand. The Boltzmann brain problem is not a puzzle about bizarre fluctuations in the distant future. It is a puzzle about the logical coherence of our cosmological theories. It forces us to ask, what does it mean for a theory to be rationally believable? What does it mean for an observation to be typical? What does it mean to be an observer at all? And the answers are not clear. Some physicists accept the vacuum decay escape. The universe will end, the brains will not accumulate, and we can trust our reasoning. This is the pragmatic resolution, and it is perhaps the most common view among working cosmologists. Some physicists accept the measure problem escape. The question of typical observers is ill-defined, the counting is arbitrary, and we should not take the Boltzmann brain ratio seriously. This is the deflationary resolution, and it has its own adherents. Some physicists accept neither. They argue that the problem reveals a genuine crisis in our understanding, that we do not yet have the conceptual tools to reason about observers in eternal universes, and that progress in physics will require developing those tools. This is the patient resolution, the resolution that waits. And some physicists, a small but persistent minority, take the problem at face value. They ask, what if we are Boltzmann brains? What if the past is an illusion, the memories are false, and this moment right now is all there is? This is not a conclusion. It is a provocation. It is a way of sitting with the uncertainty, of feeling the weight of the question, of refusing to reach for a comfortable answer before the work is done. Picture the void again. The infinite patient dark, the faint thermal glow of the De Sitter horizon, billions upon billions of years from now. In that dark, a ripple forms, particles coalesce, a structure takes shape, fragile, temporary, impossibly rare. It experiences, it remembers, it believes, and then it dissolves, leaving no trace, no record, no proof that it ever existed. Was it real? Are you? The mathematics does not know. The mathematics only calculates probabilities, waiting times, ratios of observers. The question of what is real, of what experience counts, of what memory means, lies beyond the equations. But the equations have brought us here. They have forced the question. And as we continue, we will ask what it would take to answer it. We will trace the models that physicists have built, the assumptions they have questioned, the escapes they have tried. The night is long, the void is patient, and we are only partway through. The void is patient, but the physicists are not. In offices and seminar rooms, on blackboards and in the margins of papers, cosmologists have been wrestling with the Boltzmann brain problem for more than 2 decades now. And the wrestling has produced something unexpected. Not a solution exactly, but a shift in how the problem is understood. What began as an embarrassment, a reductio ad absurdum that seemed to undermine certain cosmological models, has become a design constraint, a filter, a test that any serious theory of the universe must pass. To understand how this happened, we need to follow the argument into the machinery of modern cosmology, into the landscape of string theory, the multiverse, and the delicate business of counting infinities. This is where the Boltzmann brain problem stopped being a curiosity and became a weapon. The story picks up in the early 2000s, in the wake of a discovery that changed everything: the accelerating expansion of the universe. In 1998, 2 independent teams of astronomers studying distant supernovae found that the expansion of the cosmos is speeding up. This was not supposed to happen. Gravity pulls, matter attracts. The expansion should have been slowing down, not accelerating. But the data was unambiguous. Something was pushing the universe apart, and that something came to be called dark energy. The simplest explanation for dark energy is the cosmological constant, a term in Einstein's equations that represents the energy of empty space itself. If the vacuum has a small positive energy density, then space will expand faster and faster forever. The universe will not recollapse. It will not coast to a halt. It will accelerate, thinning out, cooling down, approaching the de Sitter state we have already described, and in that state the Boltzmann brains wait. This was the moment when the problem became urgent. Before 1998, eternal inflation was a theoretical possibility, a consequence of certain models, a scenario to be explored. After 1998, eternal expansion looked like the actual fate of our universe. The dark energy was measured. The cosmological constant was real, or something very like it, and the infinite future stretched out before us, patient and empty, with all the time in the world for thermal fluctuations to assemble every possible observer. Sean Carroll, whom we have already met, was among the first to articulate the stakes clearly. In a series of papers and lectures beginning around 2004, he argued that the Boltzmann brain problem was not a peripheral concern but a central challenge for cosmology. Any theory that predicts an eternal de Sitter future, he wrote, predicts that almost all observers in the universe will be Boltzmann brains, and any theory that makes that prediction is in tension with our own existence, or at least with our belief that our observations are reliable. Carroll's argument was sharp and uncompromising. If you take the mathematics seriously, he said, you cannot ignore the ratio. You cannot wave it away by saying that Boltzmann brains are rare or far in the future. Rare events, given infinite time, become certainties. The far future, given eternal expansion, is almost all of eternity. And in that eternity, we are outnumbered. But Carroll did not stop at diagnosis. He and his collaborators, including Jennifer Chen, Kimberly Boddy, and others, began exploring possible escapes. What would it take to build a cosmological model that does not produce more Boltzmann brains than ordinary observers? What conditions must the universe satisfy to avoid the paradox? The answers they found were surprising. They placed tight constraints on the nature of dark energy, the fate of the vacuum, and the structure of the multiverse. The Boltzmann brain problem, it turned out, could rule out entire classes of theories. It was not just a philosophical puzzle, it was a filter for physics. Consider the simplest case, a universe with a true cosmological constant. In such a universe, the vacuum energy is fixed. The de Sitter state is eternal. The fluctuations continue forever, and the Boltzmann brains accumulate without limit. This is the scenario we have been describing, and it is the scenario that produces the worst-case ratio, an infinite number of Boltzmann brains for every ordinary observer. If our universe has a true cosmological constant, and if that constant is positive, then we face the full force of the problem. But what if the cosmological constant is not constant? What if the dark energy is dynamic, a field that changes over time, that decays, that eventually vanishes? This is the quintessence scenario, named after the fifth element of medieval philosophy. In quintessence models, dark energy is not a fixed property of the vacuum but a slowly evolving field. Like a ball rolling down a shallow hill, the field can change, the expansion can change, the future can change. Some quintessence models predict that the dark energy will eventually decay to zero. The accelerated expansion will stop. The universe will coast, thin out, and cool, but it will not approach the eternal de Sitter state. Without that state, there is no infinite future of thermal fluctuations. Without the infinite future, there are no infinite Boltzmann brains. The ratio is finite. The problem is contained. This is one escape route, and some cosmologists take it seriously, but it requires fine-tuning. The quintessence field must be configured just so, decaying slowly enough to explain the current acceleration, but not so slowly that it persists forever. And the evidence so far favours a cosmological constant that does not change. The dark energy appears to be constant in time, or very nearly so. The quintessence escape may be closed. There is another escape, more dramatic and more speculative, the vacuum decay we mentioned earlier. Perhaps our vacuum is not the true vacuum. Perhaps it is metastable, a false vacuum poised on the edge of a transition to a lower energy state. If such a transition occurs, it will propagate at the speed of the light, converting the old vacuum into the new one, releasing enormous energy and destroying everything in its path. Not just planets and stars, but space itself as we know it. The laws of physics would change, the constants would shift, the universe would become something utterly different, utterly inhospitable to any observer that depends on the current laws. This sounds like a catastrophe, and in one sense it is. But from the perspective of the Boltzmann brain problem, it is a solution. If the vacuum decays, the eternal de Sitter state is interrupted. The infinite future is cut short. The fluctuations cease. The brains do not accumulate. We are no longer outnumbered by ghosts. This is the escape that many cosmologists find most compelling. It does not require fine-tuning. It does not require new fields or new dynamics. It requires only that our vacuum be unstable, a possibility that is entirely consistent with our current understanding of physics. The standard model of particle physics, in fact, suggests that our vacuum may be metastable. The Higgs field, which gives particles their mass, sits in a shallow potential well. A sufficiently large fluctuation could kick it out of that well, triggering a phase transition that would rewrite the laws of nature. The timescale for this transition is uncertain. It could be billions of years, it could be much longer. But if it is finite, if the vacuum will decay at some point in the cosmic future, then the Boltzmann brain problem has a natural resolution. The universe is not eternal. The de Sitter state is not permanent. The ratio is not infinite. We can trust our memories. Let that settle for a moment. The mathematics that predicts Boltzmann brains also points toward its own escape, a universe that destroys itself before the paradox can fully manifest. The cure is annihilation. The resolution is the end. But there is something unsettling about this escape. It depends on a feature of the universe that we cannot observe, cannot measure, cannot verify. We do not know if our vacuum is metastable. We do not know when or if it will decay. We are placing our hopes on a catastrophe we cannot see coming, a phase transition that would erase not just us but the entire observable cosmos. If this is the solution, it is a solution we can never confirm, and so the physicists continue to search. They look for other escapes, other constraints, other ways to avoid the conclusion that most observers in the universe are fluctuations in the void. And in doing so, they have transformed the Boltzmann brain problem from an embarrassment into a tool. This transformation happened most dramatically in the context of the string theory landscape and the multiverse. To understand it, we need to step back and consider what string theory says about the vacuum, or rather, what it says about vacua, plural. In string theory, the vacuum is not unique. There is not one empty space, but many. An enormous number of possible configurations, each with its own laws of physics, its own particle content, its own cosmological constant. The number of these configurations is staggering. Estimates range from 10 to the 500 to 10 to the 100,000. This is not a number you can write down in decimal form. It is not a number you can visualize. It is a landscape, a vast space of possibilities, each possibility a different universe with different rules. This is the string landscape, and in the context of eternal inflation, every point on the landscape can be realized. The inflating universe spawns bubble after bubble, each bubble a different vacuum, each vacuum a different world. The multiverse is not a hypothesis in this picture. It is a consequence of the theory. If string theory is true, and if inflation is eternal, then the multiverse exists. We are one bubble among many, one vacuum among countless others. But here is the problem. In the multiverse, the Boltzmann brain puzzle becomes even more acute. Each bubble that expands into a desistor state will produce its own population of Boltzmann brains. Each bubble that persists forever will produce infinitely many. The multiverse, far from solving the problem, multiplies it. The ratio of Boltzmann brains to ordinary observers is not just infinity. It is infinity times infinity, counted across an infinite number of bubbles. This is where the measure problem becomes critical. To compare the number of Boltzmann brains to the number of ordinary observers, you need to count them. But how do you count observers in an infinite multiverse? How do you define a ratio when both numerator and denominator are infinite? There is no obvious answer. Different counting procedures give different results. Some measures weight early observers more heavily than late ones. Some measures weight large regions more heavily than small ones. Some measures count all observers equally, regardless of when or where they exist. And depending on which measure you choose, the Boltzmann brain ratio changes. In some measures, ordinary observers dominate. In others, Boltzmann brains do. The answer depends on the question, and the question is not well defined. This is deeply unsatisfying. A physical theory should not give different predictions depending on an arbitrary choice of counting procedure. The measure ambiguity suggests that something is missing from our understanding, that we do not yet know how to think about probability in an infinite, eternal branching cosmos. But the ambiguity has a silver lining. It means that the Boltzmann brain problem can be used as a constraint. If a particular measure predicts that Boltzmann brains dominate, we have reason to reject that measure. If a particular cosmological model combined with a particular measure produces an unacceptable ratio, we have reason to reject the model, the measure, or both. The problem becomes a test. It rules things out. This is exactly how some physicists have used it. Raphael Bousso, whom we mentioned earlier, has been a leading figure in this effort. Together with collaborators like Benfrey Vogel and Yisheng Yang, he has developed measures for the multiverse that avoid the Boltzmann brain problem, measures that count only observers within a causally connected region, that weight observations by their causal proximity to a given point, that cut off the infinite future before the fluctuations can dominate. The causal diamond approach is one example. In this picture, you draw a region of space-time bounded by your past light cone and your future light cone, the region that can causally influence you or be influenced by you. Within this diamond, the universe is finite, the fluctuations are rare, and ordinary observers vastly outnumber Boltzmann brains. The ratio is not infinite, the paradox dissolves, but the causal diamond is not the only possibility. Other measures give other results, and the debate about which measure is correct, if any measure is correct, continues. The measure problem is one of the deepest unsolved problems in theoretical cosmology, and the Boltzmann brain puzzle sits at its heart, a test case, a challenge, a reminder that we do not understand how to reason about infinity. There is something almost absurd about this situation. Physicists are arguing about the proper way to count observers who may or may not exist in a future that may or may not happen in bubbles that may or may not be real. The debate sounds like medieval theology, angels on the head of a pin. And yet the stakes are serious. If we cannot resolve the measure problem, we cannot make predictions in the multiverse. And if we cannot make predictions, we cannot test the theory. The multiverse becomes unfalsifiable, a philosophical speculation rather than a scientific hypothesis. This is why the Boltzmann brain problem matters. It is not about the brains themselves. It is about the coherence of our theories. It is about whether physics can extend its reach to the largest scales and longest times without collapsing into paradox. The brains are a symptom. The disease is our ignorance. Rest with that for a moment. The night is deep now, and the void stretches out in all directions. In that void, the fluctuations continue, or they do not, depending on whether the vacuum decays, whether the measure is correct, whether the theory is true. We do not know. The mathematics has brought us to the edge of knowledge, and the edge is not a cliff but a fog. The answers are hidden. The questions remain. But the questions have a shape now. They are not formless anxieties but precise challenges. What is the fate of the vacuum? What is the correct measure? What does it mean to be a typical observer? These are questions that can be investigated, debated, perhaps eventually resolved. The physicists are working. The calculations continue, and slowly, carefully, the fog may lift. There is another thread to follow, a thread that leads not outward into cosmology, but inward into the nature of observation itself. We have been treating observers as given, as things that exist, that experience, that can be counted. But what is an observer? What makes a fluctuation in the void into a conscious being? What distinguishes a Boltzmann brain that experiences from a random arrangement of particles that merely resembles one? This is the hardest question of all. It is a question about consciousness, about the relationship between physical states and subjective experience, about what philosophers call the mind-body problem, and it is a question that physics, as currently practiced, does not know how to answer. Consider the Boltzmann brain in the void. It is a physical system, a collection of particles arranged in a particular configuration. If that configuration matches the configuration of a human brain in a particular mental state, does it have experiences? Does it feel? Does it wonder? The intuitive answer is yes. If the configuration is identical, the experience should be identical. Consciousness, on this view, supervenes on physical structure. Duplicate the structure or duplicate the mind. But this intuition leads to strange places. It means that a brain assembled by thermal fluctuation, existing for a fraction of a second in the void, has a moment of genuine experience, genuine joy or fear or confusion or peace. It means that the universe is filled with fleeting selves, minds that flicker into existence and vanish, each one as real as you are now. Or perhaps not. Perhaps consciousness requires more than instantaneous structure. Perhaps it requires history, causation, integration over time. Perhaps a Boltzmann brain, assembled in an instant, lacks the causal continuity that genuine experience requires. It has the appearance of memory without the substance. It has the form of thought without the process. It is a statue, not a sculpture, a snapshot, not a film. This is the view that some philosophers and physicists take. On this account, Boltzmann brains are not observers at all. They are mimics, physical systems that resemble observers but lack the essential ingredient, whatever that ingredient is, that makes experience real. If this view is correct, the Boltzmann brain problem dissolves. The fluctuations in the void are not observers. They cannot be counted. The ratio is undefined. But this escape is slippery. It depends on a theory of consciousness that we do not have. It requires us to say what distinguishes a genuine observer from a mere configuration of matter, and we do not know how to say it. The question of what makes something conscious is one of the oldest and most intractable problems in philosophy. It is not a question that cosmology can answer, and yet the Boltzmann brain problem forces cosmology to confront it. Here, then, is the deepest layer of the puzzle. The Boltzmann brain problem is not just a problem about cosmology or probability, or the measure of the multiverse. It is a problem about the nature of mind. It asks, what is an observer? What is experience? What is the relationship between the physical and the mental? And until we answer these questions, we cannot fully resolve the paradox. Some physicists shrug at this point. They say, the hard problem of consciousness is not my department. I calculate vacuum decay rates and inflation parameters. The question of what makes something conscious is a question for philosophers, or neuroscientists, or someone else. I will take observers as given and move on. This is a reasonable response. Division of labour exists for a reason, but it leaves the Boltzmann brain problem incompletely resolved. The physicists can calculate the probabilities. They can design models that avoid the worst ratios. They can develop measures that favour ordinary observers, but they cannot say with confidence that a thermal fluctuation in the void is not an observer. They cannot rule out the brains by ruling out their minds. And so, the question lingers. It waits in the background of the technical debates, the measure arguments, the vacuum decay calculations. It is the question behind the question, not just how many Boltzmann brains will the universe produce, but which of those brains will experience their brief flickering existence. Which of them will be someone? You can let that thought rest now. It is a heavy thought, and it does not demand an answer tonight. The void is patient. The fluctuations, if they exist, will wait, and we have more to explore. More models, more arguments, more ways that physicists have tried to make sense of this strange territory. But notice where we are. We have traced the Boltzmann brain problem from its origins in 19th century thermodynamics to its modern formulation in cosmology. We have seen how the problem sharpened with the discovery of dark energy, how it intensified in the context of the multiverse, how it became a filter for theories rather than just a puzzle to be solved. We have seen the proposed escapes, vacuum decay, quintessence, causal diamonds, alternative measures. And we have seen the deep questions that remain: the measure problem, the nature of consciousness, the meaning of typicality in an infinite cosmos. The mathematics has carried us far. It has shown us a universe stranger than intuition suggests, a future more patient than we imagined, a void more fertile than emptiness should be. And it has brought us to the edge of what we know, the boundary where physics meets philosophy, where calculation meets uncertainty, where the question of what is real remains unanswered. The night continues, the void waits, and we are not done yet. There are more threads to follow, more implications to trace, more ways to sit with the strangeness of the question. We have asked what it would mean if the math is right. Now we will begin to ask what it would mean if we can never know. The question of knowing is itself a kind of vertigo. Consider your position. You are presumably a being with memories. You remember waking this morning, or perhaps you remember falling asleep last night, the weight of your body settling into the mattress, the slow dimming of thought. You remember yesterday, and the day before, and a childhood that stretches back through years you can no longer fully recall. You remember learning to read. You remember the taste of food you ate decades ago. You remember faces, names, places, the texture of experience accumulated over time. But here is the difficulty. Every memory you possess is a physical state. It is a configuration of neurons, a pattern of synaptic connections, a particular arrangement of matter in your brain. And if a Boltzmann fluctuation can assemble a brain, it can assemble a brain with memories. The memories do not need to be accurate. They do not need to correspond to events that actually occurred. They only need to exist as physical patterns in the flickering matter. A Boltzmann brain that spontaneously assembles in the void might possess, in its brief moment of existence, what feels like a lifetime of recollection. It might remember a childhood it never had. It might remember parents who never existed. It might remember reading about Boltzmann brains in a documentary and finding the whole idea unsettling. The memories would be false, of course. They would be random configurations that happen, by chance, to encode experiences that feel coherent. But from the inside, from the perspective of that momentary observer, they would be indistinguishable from real memories. This is the epistemic horror at the heart of the problem. It is not just that Boltzmann brains might outnumber ordinary observers, it is that, if you were a Boltzmann brain, you could not know it. Let that settle for a moment. Your confidence that you are a normal observer, a being that evolved on a planet orbiting a star in a galaxy that formed through billions of years of cosmic history, rests on your memories and your perceptions. But both of these are physical states. Both can, in principle, be produced by thermal fluctuation. And if thermal fluctuations produce vastly more observers with false memories than evolution produces observers with true ones, then your confidence is statistically unfounded. You're most likely not what you think you are. This is not a claim that you're definitely a Boltzmann brain. It is a claim about what you can rationally believe given certain cosmological assumptions. If the universe is eternal, if fluctuations are common enough, if the mathematics works out the way the pessimistic calculations suggest, then the rational conclusion is disturbing. You should assign high probability to the hypothesis that your memories are false, your perceptions are unreliable, and your existence is a momentary fluctuation rather than a chapter in a coherent history. Philosophers call this kind of argument a skeptical scenario. It is structurally similar to older thought experiments. Descartes imagined an evil demon deceiving him about the nature of reality. 20th century philosophers imagined brains in vats, fed false sensory experiences by malicious scientists. The Boltzmann brain scenario is the cosmological version of these ideas, but with a crucial difference. It is not a philosophical fantasy, it is a consequence of physics. The evil demon is optional. The brain in a vat requires a vat and a scientist to maintain it. But the Boltzmann brain requires nothing except the laws of thermodynamics and enough time. If the universe lasts long enough, fluctuations will happen. They are not a hypothesis to be entertained or rejected. They are a prediction of our best physical theories. The question is only whether they are common enough to matter. And the calculations suggest that they are. In a universe dominated by dark energy, expanding forever, cooling toward equilibrium but never quite reaching it, the fluctuations add up. Over timescales that dwarf human comprehension, the rare becomes inevitable. The improbable becomes typical, and the ratio of Boltzmann brains to ordinary observers tilts, relentlessly, toward the brains. Some physicists respond to this with what might be called the sanity check. They say, obviously we are not Boltzmann brains. The hypothesis that we are Boltzmann brains is self-undermining, because if we were Boltzmann brains, our reasoning faculties would be unreliable, and we could not trust the very calculations that led us to the conclusion. Therefore, we should reject any cosmological model that predicts we are probably Boltzmann brains. This is a powerful response. It takes the absurd conclusion as evidence against the premises. If a theory predicts that you are probably a momentary fluctuation with false memories, then something is wrong with the theory. The theory has failed an empirical test, albeit an unusual one. But notice what this response requires. It requires us to treat our own existence as a data point. It requires us to say, I know that I am a normal observer, and any theory that denies this is ruled out by my knowledge. This is a reasonable move, but it is also a strong claim. It assumes that we can know, with confidence, something about our own nature that the theory calls into question. The skeptical scenarios of philosophy are designed precisely to probe this assumption. Can you know that you are not a brain in a vat? Can you know that your memories are accurate? Can you know that the external world exists as you perceive it? These questions have occupied philosophers for centuries, and there are no easy answers. The Boltzmann brain problem imports these ancient puzzles into modern cosmology and gives them new urgency. There is another way to frame the sanity check. Rather than saying we know we are not Boltzmann brains, we might say that we should assign prior probabilities that make the Boltzmann brain hypothesis unlikely. We might say that before doing any cosmological calculation, we already have strong reasons to believe we are ordinary observers. The cosmological predictions then have to overcome this prior belief. This is the Bayesian approach to the problem. It treats our confidence in our own normality as a prior probability, and it asks how much evidence would be needed to overturn that prior. If we assign high prior probability to being ordinary observers, then even a cosmological model that predicts many Boltzmann brains might not shift our beliefs very much. The evidence from our own experience would outweigh the evidence from the calculations. But this approach has its own difficulties. It requires us to justify the prior. Why should we assign high probability to being ordinary observers before doing the cosmological calculation? If the calculation shows that ordinary observers are rare, what grounds do we have for believing we are among them? The Bayesian approach shifts the problem rather than solving it. It moves the question from cosmology to epistemology, from the nature of the universe to the nature of knowledge. Some researchers have tried to dissolve the problem by arguing that Boltzmann brains are not really observers at all. The thought here is that consciousness requires certain kinds of processes, certain kinds of integration, certain kinds of duration, that a momentary thermal fluctuation cannot provide. A brain that exists for a fraction of a second, with no causal history and no causal future, might not be conscious in any meaningful sense. It might be a zombie in the philosophical sense, a physical system that looks like a brain but has no inner experience. This is a tempting escape, but it faces the same difficulty we encountered before. We do not have a theory of consciousness that tells us what physical systems are conscious and which are not. We cannot draw a line and say, systems with this property are observers, and systems without it are not. The hard problem of consciousness is precisely the problem of explaining how physical processes give rise to subjective experience, and we have not solved it. Until we do, we cannot confidently exclude Boltzmann brains from the class of observers. There is a related argument that focuses on functional integration. The idea is that consciousness depends not just on having the right physical structure, but on that structure being functionally connected over time. A brain that evolved on a planet has a history of learning, adaptation, and response to the environment. Its current state is causally connected to its past states in complex ways. A Boltzmann brain, by contrast, has no such history. Its current state is a random fluctuation, not the product of a coherent causal process. Perhaps the argument goes, this difference matters for consciousness. Perhaps genuine experience requires causal continuity, a flow of information through time, a process of integration that connects moment to moment. If so, then Boltzmann brains might be physically identical to real brains at a single instant, but different in their temporal structure, and this difference might be the difference between consciousness and its absence. This is an interesting hypothesis, but it is speculative. We do not know whether causal continuity is necessary for consciousness. We do not know what the minimum duration of a conscious experience is. We do not know whether a brain that exists for a nanosecond can have a nanosecond of experience. These are empirical questions that we cannot currently answer, and until we can, the escape route remains uncertain. Consider too the observer selection effects. If Boltzmann brains are vastly more common than ordinary observers, but have much shorter experiences, then the total amount of experience in the universe might still be dominated by ordinary observers. The measure problem again. How do we count observers? By number or by duration? By existence or by experience? If we count by experience, then a Boltzmann brain that exists for 1 second and has 1 second of experience counts much less than a human who lives for 80 years and has 80 years of experience. The ratio of Boltzmann brain experiences to ordinary observer experiences might be very different from the ratio of Boltzmann brain numbers to ordinary observer numbers, but this response has its own puzzles. It requires us to weigh experiences by duration, and it is not clear that this is the right approach. Is a 10-second experience 10 times as significant as a 1-second experience? Is an 80-year life 80 times as significant as a 1-year life? These are questions about the value or weight of experience, and they are not easy to answer. There is also the question of what counts as a single experience. If a Boltzmann brain flickers into existence with memories of a lifetime, does it have one brief experience or a lifetime of apparent experiences compressed into a moment? The memories are false, but from the inside they feel like a history. How do we count that? You can see how the problem ramifies. Every proposed escape opens new questions, new difficulties, new layers of complexity. The Boltzmann brain problem is not a puzzle with a clean solution. It is a web of interconnected puzzles, each one touching fundamental questions about physics, probability, consciousness, and knowledge. Let us return to the physicists for a moment. What are they actually doing about all this? The short answer is that they are trying to build theories that avoid the problem. They are designing cosmological models in which ordinary observers dominate, models in which the universe does not last long enough or does not fluctuate often enough for Boltzmann brains to become typical. We have already discussed some of these models: vacuum decay, quintessence, causal diamond measures. But there is a meta-level concern here. If physicists are choosing their theories partly on the basis of whether those theories avoid the Boltzmann brain problem, then the Boltzmann brain problem is functioning as a selection criterion for theories. It is shaping the landscape of acceptable cosmology. And this is a remarkable situation. Usually we test theories against observations. We make predictions, we gather data, we compare the two. A theory survives if its predictions match the data. But the Boltzmann brain problem involves a kind of prediction that cannot be tested in the usual way. We cannot survey the population of observers in the universe and count how many are Boltzmann brains. We cannot send probes to the distant future to check whether fluctuations are producing minds. The prediction is about observers who, by hypothesis, are scattered across eternity, most of them long after our civilization has vanished. So how do we test the theory? The answer, for many physicists, is that we test it against the assumption that we are typical observers. If a theory predicts that typical observers are Boltzmann brains, and we believe we are not Boltzmann brains, then the theory fails the test. Our own existence, our own apparent normality is the data point. This is a strange kind of empiricism. It uses the observer as evidence. It treats your conviction that you have a real history as information that can rule out theories, and it requires a philosophical stance on what you can know about yourself. Some physicists are comfortable with this. They argue that it is no different in principle from any other use of observation in science. We always use our experiences to test theories. We always take our perceptions as evidence. The Boltzmann brain problem just makes this explicit. Others are more troubled. They worry that using observer expectations as a filter for theories is a slippery slope. It might lead us to reject theories that are true but uncomfortable. It might lead us to privilege our intuitions over the mathematics. It might lead us to a kind of anthropocentrism, a refusal to accept conclusions that demote us from typical to exceptional. The debate continues. It is one of the liveliest areas of discussion in theoretical cosmology, though it often happens in the footnotes and sidebars rather than the main text of papers. The technical work goes on, the calculations are refined, the models are adjusted. But behind the equations, the philosophical questions persist. There is one more thread to follow here, one more way of sitting with the strangeness. It concerns the meaning of probability itself. When we say that Boltzmann brains are more probable than ordinary observers, what do we mean? Probability in physics usually refers to frequencies. We say that a coin has a 50% probability of landing heads because if we flip it many times, about half the outcomes will be heads. Probability is a statement about ensembles, about collections of events, about what happens over many trials, but the universe does not come in an ensemble. There is, as far as we know, only one universe. We cannot flip it many times and see what happens. We cannot run the cosmic history again and count the observers. The probabilities we calculate are theoretical, derived from the laws of physics and the initial conditions. They are not frequencies, but measures, assignments of weight to different possibilities. And here the measure problem returns. In an infinite universe, or an eternal one, how do we assign probabilities? If infinitely many Boltzmann brains and infinitely many ordinary observers both exist, what does it mean to say that one type is more probable than the other? The mathematics of infinity is treacherous. Infinite quantities can be compared in different ways, and the answer depends on the method of comparison. We have discussed this before, but it bears repeating in this context. The statement that you are probably a Boltzmann brain depends on a particular way of counting observers. If we count differently, the probabilities shift, and we do not know which way of counting is correct. Some researchers argue that the measure problem undermines the entire Boltzmann brain argument. If we cannot assign well-defined probabilities to different types of observers, then we cannot say that Boltzmann brains are probably in the majority. The argument rests on a foundation that has not been secured. Others argue that the measure problem is a technical difficulty, not a refutation. They believe that a correct measure exists and that when we find it, the Boltzmann brain probabilities will be well defined. In the meantime, we should take the problem seriously even if we cannot yet calculate the exact ratios. The truth is that we are in a state of uncertainty. The Boltzmann brain problem reveals how much we do not know, how many foundational questions remain open. It is not just a puzzle to be solved. It is a mirror reflecting back the limits of our understanding, and perhaps that is the most important lesson. The Boltzmann brain problem is not primarily a threat. It is not a warning that you are probably a figment of the void. It is a reminder of the depth and strangeness of the questions we are asking. It is a marker of how far physics has come and how far it still has to go. We have learned to calculate the behavior of particles and fields with exquisite precision. We have mapped the history of the cosmos from the first fraction of a second to the present day. We have discovered dark energy and dark matter and the accelerating expansion of space. We have built theories of inflation and eternal inflation and the multiverse. But we have not answered the question of what we are. We have not explained how matter becomes mind. We have not solved the measure problem or the hard problem of consciousness. We have not established what it means to be a typical observer in an atypical universe. The Boltzmann brain problem sits at the intersection of all these unknowns. It is the place where cosmology meets philosophy, where physics meets the question of existence, and it is the place where the calculations, however sophisticated, reach their limit. There is a certain humility in this. The greatest minds of our species have built theories of the universe, and those theories have brought us here to a question we cannot answer. The mathematics works, the predictions are clear, and yet we do not know what to make of them. Perhaps future generations will solve the measure problem. Perhaps they will develop a theory of consciousness that tells us which physical systems are observers and which are not. Perhaps they will discover that dark energy decays and that the universe will end before the Boltzmann brains can dominate. Perhaps they will find an escape route we have not imagined. Or perhaps they will not. Perhaps the question will remain, waiting in the mathematics, a strange attractor that pulls in anyone who thinks deeply about the future of the cosmos. Perhaps the Boltzmann brain problem is not a problem to be solved, but a feature of our situation, a consequence of taking physics seriously in a universe that does not owe us comfort. The void is patient. It has time. And we have one more territory to explore before this journey rests. We have asked what it means to know, what it means to be typical, what it means to count observers in an infinite expanse. Now we will ask what it means to live with the question, to carry the uncertainty, to be a mind in a cosmos that may or may not be what it appears. The night continues. The night continues, and so do we. There is a peculiar weight to living with a question that cannot be closed, not a puzzle waiting for cleverness, not a riddle whose answer hides behind the next experiment, but a question that may belong to the permanent architecture of thought. The Boltzmann brain problem is one of these, and now, having traced its logic, its mathematics, its evasions and its persistence, we arrive at something quieter. Not the problem itself, but the experience of holding it. What does it mean to carry this uncertainty? What does it do to a mind that takes it seriously? Let us begin with a confession. Most physicists do not think about Boltzmann brains very often. The problem lives in the corners of cosmology, in the final chapters of textbooks, in the speculative papers that push against the boundaries of what can be calculated. It is not the kind of question that occupies the daily work of laboratories. You cannot design an experiment to detect whether you are a fluctuation. You cannot build a telescope that peers into the void and counts the false observers assembling in the dark. The problem is, in a certain sense, impractical, and yet it persists. It persists because the people who think about the deep structure of reality cannot ignore it. It persists because the mathematics that got us here is the same mathematics that explains the cosmic microwave background, the distribution of galaxies, the history of the elements. You cannot accept the triumphs of modern cosmology and reject the place where those triumphs lead. The Boltzmann brain problem is not an aberration. It is a consequence, and consequences in science do not disappear because we find them uncomfortable. So how do cosmologists live with it? The answer varies. Some treat the problem as a constraint, a test that any viable theory of the cosmos must pass. If your model predicts that Boltzmann brains dominate, you revise the model. You look for mechanisms that avoid the conclusion. You design your multiverse, your measure, your initial conditions to ensure that ordinary observers remain typical. In this view, the Boltzmann brain problem is useful precisely because it is so extreme. It forces precision. It exposes the consequences of assumptions that might otherwise go unexamined. A theory that permits an eternity of empty space is a theory that must reckon with what that eternity contains. Others take a more philosophical stance. They argue that the problem reveals something important about the nature of probability itself, about the limits of counting in infinite ensembles. The measure problem, as we have seen, is not merely technical, it is conceptual. It asks us to define what we mean by likelihood in a context where the usual tools break down. Some physicists suspect that the resolution will come not from new cosmology, but from new foundations, a rethinking of how probability applies to observers, or a clearer understanding of what consciousness requires. In this view, the Boltzmann brain problem is a symptom. The disease is elsewhere, hiding in our assumptions about minds and measures and the conditions under which counting makes sense. And then there are those who simply wait. They acknowledge that the problem is real, that the argument is sound, that the escape routes are incomplete, but they suspect that the answer lies in physics we have not yet discovered. Perhaps dark energy is not constant. Perhaps the vacuum will decay. Perhaps eternal inflation does not occur, or perhaps it occurs in a way that changes the measure. The history of physics is full of problems that seemed intractable until a new framework arrived. General relativity dissolved puzzles that had plagued Newtonian gravity for centuries. Quantum mechanics revealed that the ultraviolet catastrophe, the prediction that a hot object should radiate infinite energy at high frequencies, was not a failure of physics, but a signal that physics itself needed to change. The Boltzmann brain problem may be waiting for its own transformation. There is wisdom in all of these stances, and none of them is complete. The first treats the problem as a tool, but tools require hands to wield them, and we do not yet know which model is correct. The second treats the problem as a symptom, but symptoms require diagnosis, and we do not yet have a theory of consciousness rigorous enough to say which physical systems are observers. The third treats the problem as temporary, but temporary problems have a way of lasting longer than expected, and the mathematics does not care about our patience. Let us step back then and ask a different question. What does the Boltzmann brain problem tell us about the nature of knowledge itself? Consider what we have done. We have taken the laws of thermodynamics, tested in laboratories on Earth, and extended them to the entire cosmos. We have taken the equations of quantum field theory, confirmed in particle accelerators, and applied them to the vacuum of empty space. We have taken the logic of probability, developed for dice and cards and census data, and stretched it across infinities of time and space. At every step, we have assumed that what works here works everywhere, that the principles we have discovered are universal. This assumption has been spectacularly successful. The cosmic microwave background matches the predictions of hot Big Bang cosmology to extraordinary precision. The abundance of helium and deuterium in the universe agrees with calculations made decades before the measurements. The accelerating expansion of space fits the behaviour of a cosmological constant to every decimal place we can measure. And yet, at the end of this chain, we arrive at a conclusion that seems absurd. The same principles that explain the universe now predict that most minds are delusions. The same mathematics that match the microwave background now tells us that the typical observer is a fluctuation, a momentary arrangement of particles with no past and no future, convinced of a world that does not exist. This is not a failure of physics. It is a triumph taken to its limit. The Boltzmann brain problem is what happens when successful theories are pushed into domains far beyond the conditions where they were tested. We have no direct evidence about what happens over timescales of 10 to the power of 10 to the power of 120 years. We have no experiments that probe the fluctuation dynamics of the de Sitter vacuum in the deep future. We are extrapolating, and extrapolation, however principled, is not knowledge. It is inference. It is the best guess we can make given what we know. And the Boltzmann brain problem is the place where the guess becomes unsettling. There is a lesson here about the limits of physics. The discipline has been so successful, so spectacularly good at predicting the behaviour of matter and energy, that it is tempting to believe it can answer any question. But physics is a method, not an oracle. It works by testing theories against observations. When the observations are available, it excels. When they are not, it can only offer possibilities. The Boltzmann brain problem lives in the territory where observations cannot reach. No telescope will ever see the void of the deep future. No experiment will ever probe the recurrence time of a de Sitter vacuum. We are reasoning in the dark, guided by the patterns we have found in the light. And the patterns lead here. Let us sit with that for a moment. The Boltzmann brain problem is not a discovery. It is an inference, a consequence of taking seriously the theories that have worked so far. It may be wrong. The theories themselves may be incomplete, or the extrapolation may fail in ways we cannot yet see. But if it is wrong, we do not yet know why. The escape routes are patches, not proofs. The measure problem is a gap in the foundations, not a solution. We are left with a conclusion we cannot accept and premises we cannot reject. This is a strange place to be. It is the place where confidence meets uncertainty, where the clarity of mathematics touches the fog of ignorance. And it is worth asking what this experience tells us about the practice of science itself. Science is often described as a march toward truth, a progressive accumulation of knowledge that pushes back the darkness of ignorance. There is something to this image. We know more about the universe than we did a century ago, vastly more than we did a millennium ago. The cosmic microwave background, the periodic table, the structure of DNA, the mechanism of evolution, the curvature of space-time, all of these are genuine discoveries, confirmed by observation, tested by experiment, woven into the fabric of what we can reliably say about the world. But science is also a practice of uncertainty. Every theory is provisional. Every measurement has error bars. Every conclusion is conditional on assumptions that may be revised. The history of physics is not just a story of triumphs, but also of overturnings, of confident frameworks that turned out to be approximations valid only in limited domains. Newton's gravity gave way to Einstein's. The continuous atom gave way to the quantum. The static universe gave way to expansion. Each transition preserved what worked and revealed new layers of strangeness beneath. The Boltzmann brain problem may be another of these moments. It may be the place where the current framework shows its seams, where the assumptions that have carried us so far begin to fray. Or it may be a permanent feature of any sufficiently deep cosmology, a reminder that the universe does not owe us comfortable answers. We do not know which. And not knowing is itself a kind of knowledge. It is the knowledge of limits, the recognition that there are questions we can pose but not resolve, territories we can map but not explore. Consider how this feels. You are a mind, reading these words, following the argument, trying to understand. You have memories that seem to stretch backward, a world that seems to stretch outward, a future that seems to stretch forward. All of this feels coherent, continuous, real. And yet the mathematics says that in a certain kind of universe, a universe that dark energy may be pulling us toward, most minds like yours are illusions. They flicker into existence, believe they are real, and dissolve before they can test the belief. If the argument is correct, you cannot know whether you are one of the lucky few or one of the countless phantoms. The experience would be the same. The memory would feel authentic. The world would feel solid. There is no internal test, no moment of introspection that could distinguish a real history from a fluctuation. You're left with the strange situation of being unable to rule out from the inside that you are a temporary arrangement of matter, a pattern assembled by thermal noise, carrying the conviction of a life that never happened. Let that settle. This is not meant to disturb, it is meant to clarify. The Boltzmann brain problem is not primarily a threat to your peace of mind. It is a diagnostic, a test of what we can and cannot know. If you take the argument seriously, you discover something important about the relationship between experience and reality. Experience is not self-certifying. The feeling of remembering is not proof of having experienced. The sensation of existing in a coherent world is not evidence that the world is coherent. These are facts about the structure of mind, not facts about the structure of the cosmos, and the Boltzmann brain problem makes them vivid. There is a tradition in philosophy that wrestles with exactly these questions. Descartes asked whether an evil demon might be deceiving him about everything he perceived. Berkeley asked whether the material world existed at all, or only the perceptions in the mind of God. Hume asked whether we have any reason to believe that the future will resemble the past. These are not idle puzzles. They are attempts to locate the foundations of knowledge, to find the bedrock beneath the shifting sands of belief. The Boltzmann brain problem is in some ways their descendant. It takes the doubt seriously, not as a thought experiment, but as a physical possibility. If the universe behaves as our best theories suggest, then the doubt is not merely philosophical, it is cosmological. The void, patient and empty, will generate illusions. The mathematics is clear. The only question is whether we can escape the premise. And here, perhaps, is where the Boltzmann brain problem becomes something more than a puzzle. It becomes a mirror. Look into it and you see not the void, but yourself. Not the fluctuation, but the question of what you are. The problem is not really about brains assembling from thermal noise. It is about the relationship between physics and mind, between the equations and the experience, between the cosmos and the creature that tries to understand it. We have built theories of extraordinary power. We have explained the behavior of matter from quarks to galaxies, from the first second of the universe to the present day. But we have not explained how matter becomes aware. We have not said what it is about certain arrangements of particles that gives rise to experience. We have mapped the physical correlates of consciousness, the neural pathways, the biochemical processes, the electrical signals. But we have not closed the gap between the objective and the subjective. The hard problem of consciousness remains hard. And into this gap, the Boltzmann brain problem pours its questions. If we cannot say what consciousness is, how can we count conscious observers? If we do not know which physical systems are minds, how can we calculate their probabilities? The Boltzmann brain argument assumes that a brain-shaped fluctuation would be conscious, would have experiences, would believe itself real. But this is an assumption, not a derivation. We do not have a theory that tells us whether a sudden assemblage of neurons, unconnected to a body or a history, would experience anything at all. We are extrapolating not just from physics but from intuition, from the sense that a thing that looks like a brain would think like a brain. Perhaps it would. Perhaps consciousness is substrate independent, arising wherever the right patterns occur regardless of their origin. In that case, the Boltzmann brains would be minds, and the problem would be as severe as the mathematics suggests. But perhaps it would not. Perhaps consciousness requires continuity, or interaction with an environment, or a particular kind of causal history. In that case, the fluctuations would be zombies, physical duplicates of thinking beings that do not think, patterns without experience. The problem would dissolve, not because the brains would not form, but because they would not be observers. We do not know. And this not knowing is different from the measure problem, or the decay of dark energy. Those are questions about physics, about how the universe will behave over cosmic time. This is a question about mind, about what it takes for experience to exist. The Boltzmann brain problem sits at the junction of two mysteries, and neither one is close to being solved. Let us rest here for a moment. The journey has been long. We have travelled from Boltzmann's 19th century intuition about entropy to the de Sitter vacuum of an accelerating cosmos, from the Poincaré recurrence theorem to the measure problem of eternal inflation, from the probability calculus of typical observers to the philosophical puzzle of consciousness. At every stage, the problem has refused to close. Each escape route has led to new questions. Each solution has brought new assumptions. And now we stand at the edge of what can be said, looking out into the uncertainty. There is peace in this if you allow it. The universe is strange. It does not bend to our expectations or our comfort. The same mathematics that gives us the triumph of the cosmic microwave background gives us the paradox of the Boltzmann brain. We cannot take one and leave the other. They are woven together, threads in the same fabric. And perhaps that is all right. Perhaps the goal of understanding is not to make the strangeness disappear, but to hold it clearly, to see it for what it is. The Boltzmann brain problem is a reminder that we are not finished. Physics is not finished. The questions that matter most, about time, about entropy, about mind, about existence, remain open. We are travellers in a landscape that has not been fully mapped. The night is long, the stars are far, and we're still learning what it means to be here, asking these questions, wondering what comes next. The void is patient, it does not hurry. The fluctuations assemble and dissipate on timescales that dwarf the age of galaxies, and we, for our brief moment, have the peculiar privilege of glimpsing the structure. We cannot prove that we are not dreams. We cannot calculate with certainty what the far future holds. But we can hold the question, turn it over in our hands, feel its weight. And in that holding, there is something like understanding. Not the understanding of closure, but the understanding of recognition. We see what we do not know, we name the limits, and we continue. The night continues, and there is still one more territory to cross before we rest. We have asked what it means to know, what it means to be typical, what it means to live with uncertainty. Now we will ask, finally, what it means to be here, in this moment, carrying all of this, a mind in a cosmos that remains, despite everything, precisely what it is. A mind in a cosmos that remains, precisely what it is. Let that phrase settle. It sounds like acceptance, and perhaps it is, but acceptance of what exactly? Not of resolution. We have found no tidy answer, not of comfort. The mathematics still threatens to dissolve our certainty about the most fundamental fact we believe we possess, that we are real, that our memories are true, that the world we perceive is there. What we are accepting, if we are accepting anything, is the shape of the question itself. And that shape is beautiful, in the way that all honest shapes are beautiful. Think of where we began. Ludwig Boltzmann, in the late 19th century, struggling with a puzzle that seemed almost philosophical. Why does time have a direction? Why does entropy increase toward the future and not the past? The equations of physics are symmetric. A ball rolling down a hill and a ball rolling up a hill obey the same laws, just run backward. And yet we experience only one direction. Milk stirs into coffee. It never unstirs. Ice melts. It never unmelts. Boltzmann saw that the arrow of time was not written into the fundamental laws. It was written into the boundary conditions, into the fact that the universe started in a state of extraordinarily low entropy, and everything since has been a long, slow slide toward equilibrium. That insight was revolutionary. It remains revolutionary. The arrow of time is not a law. It is an accident of beginnings. And once you accept that, you must ask, why those beginnings? Why did the universe start so far from equilibrium? What arranged the initial conditions so precisely that 14 billion years later, galaxies would form, stars would burn, planets would cool, and minds would arise to wonder about entropy? We still do not have a complete answer. The low entropy of the early universe is one of the deepest unsolved problems in cosmology. We know it happened. We measure its consequences in the cosmic microwave background, in the distribution of matter, in the very fact that anything interesting exists at all. But we do not know why. Some physicists hope that a theory of quantum gravity will explain it. Others suspect that it is a brute fact, a starting condition that simply was, requiring no deeper explanation. And still others, following the logic that led us to the Boltzmann brain, have wondered whether the low entropy beginning was itself a fluctuation, a temporary dip in the eternal sea of equilibrium, a statistical accident that happened to produce a universe that looks like ours. You see the recursion. The question of why entropy was low becomes the question of whether entropy is always low somewhere, in the infinite expanse of time or space, and whether we are simply the observers who find themselves in one of those rare pockets. The anthropic reasoning that we traced earlier, the selection effect. You cannot observe a universe that does not permit observers, so you find yourself in one that does, no matter how improbable that universe might be. It sounds almost tautological, and in a sense it is, but it has consequences that we cannot ignore. One of those consequences is the Boltzmann brain. If low entropy regions can fluctuate into existence, and if observers are what matter for the anthropic filter, then the question becomes which observers are more common. The honest answer, according to the mathematics, is that small fluctuations are more common than large ones. It is easier to fluctuate a single brain than an entire cosmos. It is easier to fluctuate a brain with false memories of a cosmos than to fluctuate the cosmos those memories seem to remember. And if you accept the logic of typicality, if you believe that you should reason as if you were a randomly selected observer from the set of all possible observers, then you should conclude that you are almost certainly a Boltzmann brain, almost certainly a dream, almost certainly a fluctuation, almost certainly something that will dissolve back into the equilibrium from which it came, its memories false, its perceptions illusory, its sense of continuous existence a trick of the mathematics. This is the conclusion that physicists find unacceptable, not because it is impossible, but because it is self-undermining. A theory that predicts you are almost certainly wrong about everything cannot be rationally believed. It soars off the branch it sits on. And so, the Boltzmann brain problem becomes a constraint, a test that any cosmological theory must pass. If your theory predicts too many Boltzmann brains, your theory is in trouble. We have traced how cosmologists respond. Some, like Sean Carroll and his collaborators, design models with a decaying cosmological constant, universes that eventually escape the de Sitter phase and collapse or transition into states where fluctuations cannot accumulate forever. Others adjust the measure, changing the rules for how we count observers across infinite time or infinite space. Still others question whether Boltzmann brains would truly be conscious, whether the patterns that fluctuate into existence would have experience or would be mere arrangements of particles, philosophical zombies in the void. None of these solutions is fully satisfying. None of them closes the problem with the clean finality of a mathematical proof. They are strategies, workarounds, ways of living with a paradox that will not go away. And perhaps that is appropriate. Perhaps the Boltzmann brain problem is meant to remain open, a permanent reminder of what we do not understand. Let us ask then what it would mean if the problem is real, not a puzzle to be dissolved by clever definitions, but a genuine feature of the physical world. What would it mean if the mathematics is right? It would mean that consciousness is fragile, that the experience of being a unified self in a coherent world is balanced on a knife's edge between two abysses. On one side, the abyss of non-existence, the overwhelming probability that most configurations of matter do not give rise to experience at all. On the other side, the abyss of false existence, the smaller but still vast probability that some configurations give rise to experience built on lies, memories of events that never happened, perceptions of worlds that are not there. We walk between these abysses every moment. We do not feel the edge. The ground beneath us seems solid. The sky above us seems real. But the mathematics says the ground is thin, far thinner than the intuition suggests. Most of the territory is void. Most of the observers, if we count across eternity, are dreams. And yet here we are, asking the question, tracing the argument, holding the paradox in our hands. That too is part of the picture. Whatever we are, however we came to be, we are the kind of thing that can wonder about its own existence, that can follow a chain of reasoning from entropy to equilibrium, to fluctuation to self-reference and back again. We are not merely experiencing, we are reflecting on experience. We are asking whether the experience is trustworthy, and that capacity for reflection is itself remarkable, regardless of the answer. Consider what it takes to ask whether you are a Boltzmann brain. You must have the concept of probability, you must have the concept of fluctuation, you must have the concept of entropy, of equilibrium, of eternal time. You must be able to hold a hypothetical scenario in your mind and reason about it, to weigh evidence, to follow logic, to accept conclusions that feel uncomfortable. These are not simple abilities. They are the product of billions of years of evolution, or if the skeptical hypothesis is true, they are the product of an extraordinarily unlikely fluctuation that happened to include not just a brain, but a brain capable of abstract reasoning, a brain that carries memories of learning physics, a brain that feels the weight of the argument it is encountering. Either way, we are extraordinary. Either we are the culmination of a cosmic process that began with low entropy and unfolded through time, or we are the rarest of fluctuations, a pocket of coherence in an ocean of noise. The mathematics does not tell us which. The mathematics only tells us that the first option, the comforting option, is not guaranteed. It must be earned. And how do we earn it? By designing theories that avoid the Boltzmann brain conclusion, by understanding the cosmological constant, the measure problem, the nature of consciousness, by pushing the frontiers of physics until we find a framework in which our existence is not a paradox. We do not have that framework yet. We are still in the middle of the journey. But the fact that we are trying, the fact that we recognize the problem and struggle with it, is itself a kind of answer. Not an answer to the question of what we are, but an answer to the question of how we should proceed. We proceed by taking the problem seriously. We proceed by not looking away. There is a famous thought experiment in philosophy called the brain in a vat. Imagine that your brain has been removed from your body and placed in a vat of nutrients. Wires connect your neurons to a supercomputer that feeds you a perfect simulation of reality. Everything you perceive, every touch, every sight, every sound, is generated by the computer. You have no way of knowing. The simulation is flawless. Your memories of your body, your past, your world are all part of the program. Are you really sitting wherever you think you are sitting, or are you a brain in a vat dreaming that you are somewhere else? The Boltzmann brain problem is a cosmological version of this thought experiment, but with a crucial difference. The brain in a vat is created by a deceiver, an external agent with a purpose. The Boltzmann brain is created by physics, by the impersonal grinding of fluctuations over unimaginable time. There is no deceiver. There is no purpose. There is only probability, playing out across eternity, assembling every possible configuration of matter, including configurations that look like you, that feel like you, that are convinced they are you, and that are nonetheless not what they believe themselves to be. This lack of intention makes the problem harder, not easier. A deceiver might be outwitted, a purpose might be understood. But physics has no agenda. The fluctuations do not care whether you are real or false. They do not care whether you suffer or flourish. They simply happen in the patient way that all physical processes happen, following the laws without malice or mercy. We are left then with a strange kind of hope. Not hope that the problem will disappear, but hope that we can learn to live with it, to incorporate it into our understanding without losing our footing. The greatest scientists have always been able to hold uncertainty without flinching. They have been able to say, "I do not know," and to continue working. The Boltzmann brain problem demands that same courage. We do not know if we are real. We do not know if our memories are true. We do not know if the universe we perceive is there. And we continue. Let me offer you one more way of holding this. Think of the problem not as a threat to be neutralized, but as a gift to be received. We have been given the tools to ask a question that most minds never ask, that most configurations of matter could never ask. We have been given the concepts, the training, the leisure, the strange accident of existing in a technological civilization at a moment when cosmology has advanced far enough to make the question precise. Whatever else we are the inheritors of that tradition. We stand on the shoulders of Boltzmann, of Poincaré, of Carroll and Albrecht, and the countless others who pushed the argument forward. We hold their work in our hands, and when we hold it, we see something astonishing. We see that the universe, as best we understand it, is not a simple place. It is not a clockwork mechanism ticking toward a known conclusion. It is a vast, strange, possibly eternal expanse in which low entropy beginnings and high entropy futures and thermal fluctuations and conscious observers and false memories and true ones and everything in between all coexist, woven into a fabric that we are only beginning to glimpse. The Boltzmann brain is part of that fabric. It is not an error in the mathematics. It is a feature. And our task is not to erase the feature, but to understand it well enough that we know where we stand. Perhaps we stand on solid ground. Perhaps the low entropy of the early universe is explained by something deeper, something that makes Boltzmann brains rare or impossible. Perhaps the cosmological constant decays, or the measure problem has a solution, or consciousness requires continuity in a way that fluctuations cannot provide. Perhaps, when all the work is done, we will look back and see that the threat was never as severe as it seemed, that the mathematics bends toward coherence rather than chaos. Or perhaps we stand on thinner ground than we imagined. Perhaps the problem remains, a permanent feature of any eternal cosmos, a reminder that certainty is not given but earned, and not always earned completely. Perhaps we must live with a residual doubt, a whisper at the edge of awareness that says, you do not know for certain, you cannot know for certain, and that is simply how it is. Either way, we are here now. The night is quiet. The stars, if there are stars, are far, and we have traced an argument from the 19th century to the 21st, from thermodynamics to cosmology to philosophy of mind, and found that the questions do not end. They never end. That is the nature of the deepest questions. They open into each other endlessly, and the opening is the point. So rest with that. Not with an answer, but with the shape of the inquiry. You have followed a thread through the labyrinth, and the thread has led you here, to this moment, to this awareness of what is not known. The void is still patient. The fluctuations still assemble and disperse on timescales that make galaxies seem brief. And you, whatever you are, have held the question long enough to feel its weight. There is something sacred in that. Not sacred in the sense of religion or ritual, but sacred in the older sense, set apart, marked as significant. To ask whether you are real is to take existence seriously. To follow the argument wherever it leads is to honour the tradition of honest inquiry. To sit with uncertainty without demanding premature closure is to grow into the kind of mind that can face the universe as it is, not as we wish it to be. We do not know why the universe began with low entropy. We do not know whether the cosmological constant will decay. We do not know how to count observers across eternal inflation. We do not know what consciousness is or where it arises. We do not know if we are typical or atypical, dreams or dreamers, fluctuations or the products of history. We do not know, and in the not knowing there is room. Room to wonder, room to investigate, room to hold the strangeness gently, without forcing it into shapes it does not fit. The Boltzmann brain problem is not a curse, it is an invitation. It invites us to take the mathematics seriously, to follow the implications wherever they lead, to remain humble before the vastness of what we do not understand. The night continues. It will continue long after this moment passes, long after every moment passes, stretching toward a future we cannot see and may not be able to imagine. The equilibrium waits, patient as it has always been, the final state toward which all entropy tends. And in the meantime, here, now, there is this, a pattern that wonders, a configuration that asks, a mind that holds the question and does not let go. That is enough. Perhaps it is everything. The silence out there is not hostile. It is simply vast, vaster than we have words for, vaster than our models can fully contain. And we are a small thing in that vastness, a brief arrangement of matter and energy and information that has somehow come to contemplate its own existence. Whether we are the product of cosmic evolution or the product of cosmic accident, we are here, we are asking. And the asking itself is a kind of answer, the only kind that may be available to us. So let the argument rest, let the paradox remain open, a door that does not close, an invitation to everyone who comes after us. The Boltzmann brain problem is not finished. It may never be finished. And that is all right. The greatest problems are the ones that stay with us, that shape our thinking, that remind us how far we have come and how far we have yet to go. The void is patient. We are patient too in our way. And the question lingers, soft as starlight, present as breath, as old as entropy and as new as the next thought. What, in the end, are we? The darkness does not answer. It never answers. But it holds the question, as it holds everything gently without judgment, for as long as time continues to unfold, and that perhaps is peace enough for one night.